Hello. Today's topic, again, this is the second portion of lecture number 2. And so in this unit, we are going to focus on energy metabolism. So let me just get our PowerPoint ready here. So again, we've kind of covered the basics of the physiology associated with digestion, and now we're going to take it a step further and talk about what happens to those nutrients once they have been absorbed within the body. And that's essentially what energy metabolism is going to look at, is our ability to utilize those nutrients in a few of our energy pathways. Okay. So again, a couple simple rules to keep in mind when we think about the metabolic processes. Energy is dynamic state and it's related to change. So when we think about energy and how we can utilize it, essentially we cannot create or destroy energy. We can simply transfer it from various forms, right? So again, bioenergetics is a flow and exchange of energy within a living system. So again, as I mentioned, we don't create energy and we don't destroy energy. We can simply just transfer it into various forms. Okay. So energy metabolism can be defined as how your body transforms, uses, and stores energy within the body. So again, when we think about what is bioenergetics as it relates to exercise, it's important for us to understand why we need to know this, or why is this important to us as it relates to nutrition. So one major limitation in exercise capacity is dependent on the rate at which we can extract or utilize these various energy systems. So how quickly can we transfer energy from one form into our usable form, which is known as ATP, right? So again, we want to look at these pathways, and we want to understand how we can sort of upregulate those pathways so that our athletes can improve their performance. So again, this is just one of those key pieces that we need to understand in order for us to really optimize sport performance for our athletes. So one of the components that's important when we think about, energy metabolism and this process of bioenergetics is something known as an enzyme. And an enzyme is basically this little, think of them as a coach, basically, that's going to allow us to transfer a molecule from one form into another. And the enzyme doesn't necessarily like change the process, or the enzyme isn't like consumed during the process. It simply stands there and helps the process to be sped up. Okay, so again, think about our role as a coach. We want to improve the efficiency of our athletes, and that's exactly what an enzyme does. It's going to improve the efficiency and the speed at which one of these processes can occur. So how does training affect the rate of energy conversion during exercise? Well, assuming that we're doing the right things in practice, we should be able to enhance the rate at which we can convert energy into our usable form, which is known as ATP. Okay, so again, we can spend a lot of time in our sport physiology class talking exactly about how that occurs and how we can sort of optimize our workout so that we are ensuring that we're upregulating the appropriate systems associated with each sport. So we basically have three energy systems. And again, these basic energy systems are going to allow us to convert food that we've consumed into our most basic form of energy, which is known as ATP. Okay, so there are essentially three different ways in which we can do this. And again, that's going to come up on the next slide. But the processes are the ATP phosphocreatine system, the glycolytic system, and the oxidative system. Okay. In order for us to utilize these pathways, basically we're going to take different nutrients. So whether it's carbohydrates, fats, proteins, etc., usually carbs and fats are our main sources, but we're going to break those down into ATP. And then ATP is hydrolyzed. Let me get my little pointer up here. It's hydrolyzed with the enzyme ATPase. Okay, and so ATPase basically allows us to add water, that's the hydrolyzed part, to this ATP molecule, and that's going to allow us to basically liberate the energy that we need in order to do basically every task within the body. Okay, so as I mentioned, 3 different ways in which we can get this ATP. So we have the ATP phosphocreatine system, the glycolytic system, which is also known as anaerobic glycolysis, might also be called like the lactic acid system in some sources as well. And then the oxidative system or the aerobic system. And again, that's going to be the most complex of the 3, and that'll involve a process known as oxidative phosphorylation, or the addition of, or the consumption, the addition of oxygen in order for us to kind of liberate that ATP. Okay, so regardless of which energy system that we use, ATP is the end product. Okay, the number of ATP that we gain out of each of these metabolic pathways is going to vary greatly depending on the system, right? So again, ATP can be hydrolyzed into something known as ADP. And again, that the hydrolysis process is what breaks a bond, which allows us to liberate that energy that we mentioned. Okay, so let's start with the first energy system, which is known as the ATP-PCR system, or the ATP phosphocreatine system. Okay, so the P stands for phospho, and then CR is the creatine portion. Okay, this system is important for us. It's the fastest of our energy systems, so it can give us energy that'll last anywhere from 10 to 12 seconds in duration. And this system is very easily accessible, so it's very, very fast in nature. It can be very powerful, therefore. And also, it doesn't require us to utilize any oxygen. Okay, it's the most simple of the 3 systems that we have. So let's look at how it works. So basically, I'm going to take this ATP molecule, and again, I didn't tell you this, but let me get my little pin going here. ATP stands for adenosine triphosphate. So basically, I have this adenosine molecule, and then I have 3 phosphate bonds. Tri means 3. So I have 3. Bonded molecules. Okay, so in order for me to get energy, I have to cut off one of these phosphates. Okay, so as I nip off this phosphate through the use of the enzyme ATPase, that will create adenosine diphosphate. So di means I have 2 phosphate bonds now, 1 free floating phosphate molecule. And again, the liberation of this bond that we just mentioned releases the energy. And we use that energy to do like everything within the body. So again, it's going to allow us to have contraction of the muscles, so allow us to have movement occur. It also does a lot of things that we don't maybe cognitively think about, like the contraction of the muscle within the heart, or the contraction of smooth muscle, which allows us to digest our foods. So those are just a couple examples of other factors or other things that are going on in the body that are maybe out of our conscious control, but also important as it relates to energy utilization. Okay, so again, we'll release energy when we break that phosphate bond. Okay, so now what happens with that ADP molecule? Okay, so I've got this ADP we just mentioned, and in order for me to get more energy out of it, I need to add phosphate, this phosphocreatine piece to it. So basically, what I'm going to do is I'm going to take this molecule, which is creatine, and it also has a phosphate bond. Okay, and I'm going to split those apart. So now I have creatine and a free-floating phosphate. And now I'm going to take this phosphate molecule and I'm going to hook it back on to the ADP. Okay, so the addition of the phosphate, which we stole from the creatine phosphate or the phosphocreatine molecule, allows me to regenerate ATP. Okay, once I have it back in the form of ATP, I can start the process over again. I can nip off a phosphate with the use of the ATPase molecule, and that'll cause me to liberate energy. Okay, so essentially, the more phosphocreatine that I have, the greater the capacity of this particular system. Okay, so that's what's going to determine whether I can make it 10 seconds or whether I can make it 12 seconds with the use of this system. Has to do with how much of this molecule I have within the muscle. Okay. Many of you have likely heard of the supplement creatine. Okay. And when I take creatine supplementation, like if I, did that as part of my, weightlifting program or whatever, that's going to enhance. Oh, let me get my little pointer here. That's going to enhance the amount of phosphocreatine that I have, which allows me to enhance the amount of ATP I produce within the system. Okay, so again, if I'm lifting weights, for example, okay, and I have more of this phosphocreatine available, I can lift or maintain my intensity for a prolonged period of time. So instead of being able to lift, let's say 8 reps at 200 pounds, for example, with the use of this supplement, I'm now able to do 10 reps. Okay. And so at the end of the day, this is going to allow me to overload my body more and therefore allow me to enhance my performance to a greater extent. We'll talk in a greater detail about ergogenic aids a little bit later in this course, but this is just one example of how that ergogenic aid, how that supplement actually works within the systems. Okay, so how much energy can we get from this system? Again, I would say this system maxes out between 10 to 12 seconds, depending on the training status of the individual. Okay, so we can upregulate that phosphocreatine level naturally without the use of supplements. And again, that might allow us to get to that 12-second mark, okay? Or I can utilize a supplement, which would also help me to get to that particular point. Okay, so how much energy? Again, it ranges from 10 to 12 seconds, depending on the fitness status of that individual. What are the pros and cons of using this system? Certainly a pro is that it's very quick, right? So we can get this energy very fast and it allows us to produce a large amount of power because of the speed at which this process can occur. The con of this system is it only lasts 12 seconds, right? So again, that can certainly be a negative for us in a variety of sports where we need to go longer than 12 seconds, right? So pros, it's very powerful, very fast. Cons, it's easily fatigable. It can only last us for 12 seconds. Okay. So the next system is known as the glycolytic system, and this is going to start with the breakdown of one glucose molecule or one sugar molecule. And basically, we're going to break down the sugar molecule into something known as pyruvic acid. Sometimes it's called pyruvate. Okay, and this process is anaerobic in nature, which means that we are not using oxygen in order for this process to occur. Okay, we get a yield of 2 to 3 ATP out of the deal. We also produce something known as NADH. Oops. Oh, come on now. NADH, which will be important for us in a later pathway. So kind of keep that in mind as well. And so that we can understand the complexity of this system, it requires us to convert that glucose molecule into 10 to 12 different kind of like intermediate steps before we get to that final product of pyruvic acid or pyruvate, whichever you prefer to hear it called. Okay. Again, I'm not going to like really quiz you on each of these steps or anything like that, but again, keep in mind that it is fairly complex. And again, it does require us to go through 10 to 12 different steps. But basically what I want to do is I'm going to take glucose and I'm going to convert it into all these intermediate products in order for me to, at the end of the day, end with 2 pyruvic acid molecules or 2 pyruvate molecules. Okay, so again, I don't know why some of these images are blurry, but I'm sorry about that. So again, I take that sugar molecule, which we said was glucose, I convert it into pyruvate or pyruvic acid, and then I have 2 options. I can either choose an anaerobic pathway, which is this side, or I can choose an aerobic pathway, which is this side. Okay, so let me talk about aerobic first. Okay, so if oxygen is available and if I don't need energy at a super quick rate, okay, I will choose the aerobic pathway. Okay, and so pyruvate will be converted into acetyl-CoA, and then it will enter into those aerobic pathways known as the TCA cycle. All right, so I will choose this pathway. The body wants to choose the aerobic pathway. Okay, if I'm doing something with a higher intensity, and I like max out the speed at which I can use this pathway, then I'm also going to jump over to this side. And this is going to allow me to increase the speed at which I can get energy, basically. Okay, so again, I'll choose this pathway first, and let's say I can get, again, these are arbitrary numbers, but let's say I can get 50 ATP molecules a minute out of this pathway. Okay, but let's say I'm running, for example, and I'm running at a moderate pace and I need 42 ATPs per minute. I can use the system. That's a nice steady intensity and no issues here. I can just use the system and it's nice and moderate. Okay. Let's say there's a big hill up ahead and all of a sudden now I need more ATP than just those 42 per minute that I was using at my moderate pace. So let's say now I need 65. Okay, so again, we said that we can only get 50 out of this pathway. So I'm going to get 50 here, and then I need that extra 15 in order to get me to 65. So I'm going to rely on this system in order to get that extra 15, if that makes sense. Okay, so again, body prefers to choose aerobic in nature, but if I need more energy than that, then I'm going to choose this anaerobic pathway. And what happens with this anaerobic pathway is now I'm going to take pyruvate, or that pyruvic acid, and I'm going to convert it into lactate. And that can become an issue for us for a variety of reasons. But let's take a look at what's going on here. Okay, so I take that pyruvate molecule and I convert it into something known as lactic acid. And lactic acid is very chemically unstable, so it doesn't like to be in this chemical configuration. So almost as quickly as it's converted into lactic acid, it will reconfigure itself into a lactate molecule and one hydrogen molecule. Okay, and the issue with this is that this hydrogen molecule is very acidic in nature, and your body doesn't like to have a change in its acidity. Having a bunch of acidic molecules is bad. This hydrogen molecule is what makes you feel that burning sensation in your muscles if you're lifting really hard, for example, or if you're running up a hill, or if you are a track person, if you've ever run a 400 meter race. And you get to, maybe the last 50 meters or so, and it feels like you're running in quicksand, basically. You have hit the mark where you have this accumulation of this hydrogen molecule, and that causes a super acidic feeling. Your body doesn't like it. Okay, but what I'm trying to do is I'm going to convert this pyruvate into lactate, and therefore I can get this lactate out of that muscle where I was producing ATP, like the muscle, like in your leg, for example, if you were running. Okay, and so I can throw this lactate and this hydrogen molecule into the bloodstream, and now it's not my problem if I'm a muscle cell, for example, and I can continue to produce energy because I got this acidic molecule out of my control, basically. Okay. So again, what are the pros and cons of this particular system? The anaerobic glycolytic system will allow us to get energy for up to 90 seconds or so if you're a highly trained individual. So we can utilize this system. I would say 60 to 90 seconds is a good range for us to kind of maximize the system. Again, if I'm a highly trained athlete using this system, for example, if I'm a mid-distance runner in track and field, I run 400s or 800s. So again, my races are between 45 to 230, 45 seconds to 230 for duration. Again, I'm going to really kind of maximize the use of the system. Okay. Other athletes that are strong anaerobic glycolytic athletes would be wrestlers. Even though a wrestling match lasts 7 minutes, there is some intermittent, stops and starts within any given match. And so therefore, we're really highly utilizing this system. And we're also hoping that, with each of those stops, we can kind of regenerate the system so that we can stay in one of those higher intensity energy systems as opposed to jumping down to the oxidative system or the aerobic pathway. Okay. So again, pros and cons of using the system: it can last us 60 to 90 seconds depending on our training status. It's moderate in regards to its power potential. Okay, so again, we said that ATP phosphocreatine was our most powerful system. This system is kind of like intermediate in relation to power. So think about this system as kind of like your 90% intensity, whereas that ATP phosphocreatine system was 100% everything that you possibly can give. Okay, so again, we think about pros and cons. It's intermediate in its fatigue level. It's also intermediate in regards to how much power it can produce. Okay, one other con associated with this system, and one that I didn't mention in the ATP phosphocreatine system, this system has to use carbs. Okay, so it cannot use fats, it cannot use proteins, it absolutely has to start with carbs in order for us to activate this pathway. Same thing with the ATP phosphocreatine system. We absolutely have to have carbs in order for that system to run. Okay, let me say that again. These first two energy systems, if you want to do anything with high intensity, we absolutely have to have the appropriate amount of carbs in order to do so. Okay, so as a coach, we have got to promote carbohydrates and good sources of carbohydrates in order for us to be able to do high intensity things. Okay, so that is super important. If there's one takeaway you get out of this class, it's that if we want our athletes to perform at a high intensity, they have to fuel themselves appropriately with carbohydrates. Again, I already mentioned it. What are some sports that this system would be important for us? Certainly, like a mid-distance runner in track and field. Certainly, wrestling would be another example. Swimming. If I did any of those kind of intermediate events, maybe like a 100, 200, something in that range. Where I may be swimming 1 to 2 minutes in duration. Those sports would be highly reliant on this system. Again, you think about a sport like basketball, for example. Is there ever a time where I need to run up and down the court for a minute really without stopping? Yeah, likely. If there's a couple fast breaks or whatever, I will be relying on the system. It's really hard for us to quantify intermittent sports such as basketball, football, soccer, for example, because each game is going to be different. And also, if we look at, each type of player within the team, their demands are going to be different as well. What a linebacker is doing versus a wide receiver, significantly different as it relates to metabolic demand. However, if I were to kind of give you some key sports, I would say basketball and soccer, this would be pretty important. Football, I would say, is going to be more of a true ATP-PCR type of sport. They're not going to do a whole lot longer than 45 to 60 seconds in any given time without having a break before they come back and have a second play or whatever. So. Okay. The last system to talk about, the most complicated of the three, is known as the oxidative system. And this system is the only system that's going to use oxygen, which is where it gets its name, the oxidative system. And so the body is going to break down energy in order to produce ATP. This system involves 3 different processes. So we're going to do aerobic glycolysis, the Krebs cycle, and then lastly, the electron transport chain. Okay. This system is slower to be activated, but it has the greatest potential when we think about fatigue resistance. Okay, so this system can last us a long time before it gets tired out. Okay. Again, as we kind of mentioned, what's the difference between that anaerobic and the aerobic pathways as it relates to glycolysis? So again, for both processes, glucose will be broken down into pyruvic acid. That's the process of glycolysis. And the anaerobic pathway, it will end with us producing lactic acid, which we know will eventually be converted into lactate. Okay. With aerobic glycolysis, we're going to turn that glucose into pyruvic acid, and then it will be converted into acetyl-CoA, where it can then enter into the Krebs cycle. So acetyl-CoA is the next step after the pyruvic acid. Okay. Again, I really want us to understand the difference between the aerobic and anaerobic pathways as it relates to glycolysis. Again, both of them start with a sugar molecule or glucose molecule that's converted into pyruvate. The aerobic pathway will choose acetyl-CoA, and the anaerobic pathway will choose lactate. And again, we'll only choose that anaerobic pathway if we've already maxed out the aerobic pathway. Okay. So again, we'll take that pyruvate molecule and we are going to move it into the mitochondria, which maybe you remember from high school biology. as the powerhouse of the cell. And essentially what happens within the mitochondria is we're able to do all these aerobic energy production pathways, okay? So I'm gonna take the pyruvate molecule, I'm gonna bring it into the mitochondria as I convert it simultaneously into this molecule known as acetyl-CoA. And once I'm inside the mitochondria, I can do all this cool shit from an aerobic standpoint. So let's take a look. Okay, the first, or I guess not the first, the second part of this aerobic pathway, the first was that glycolytic pathway. Okay, now I brought that acetyl-CoA into the mitochondria, and I entered this citric acid cycle, which is also known as the Krebs cycle. Okay, and think of this as like a recipe. Okay, so I'm going to add in all these little things. In order for me to get a net gain of ATP, I'm also going to produce something known as NADH and FADH. I don't see any FADH in this image, but again, I'm going to produce these NADH molecules and FADH molecules, which will come in later. We'll cache those in the next step. But think about this as like a recipe for chocolate chip cookies. Okay, now if I wanted to make chocolate chip cookies, okay, lots of different ways I can do this, right? So let's say at my house, I play this game where like I don't have all the ingredients that I need. What can I substitute in because I don't have any butter, for example, okay? Well, I don't have any butter. Could I still make those chocolate chip cookies? Yeah, I can. And what might I be able to substitute, you know, the butter for? Well, I could use like vegetable oil instead. Okay. Maybe I don't have any eggs, and so what could I use instead of eggs? Well, I've got some applesauce, so maybe I could use applesauce instead of the eggs. Okay, so there's lots of different substitutions that I can do in order to make chocolate chip cookies. The same is true in this system. Okay, so I can substitute in some of these intermediates in order for me at the end of the day to still get the same products. Okay, so this is the first time I'm able to use the first time I'm able to use fats, and it's the first time I'm able to use proteins as a fuel in order to get energy. Okay, so I can insert in some fats, I can insert in some proteins if I need to in order to make my recipe work. Okay, but the one thing I absolutely need and I cannot substitute if I want to make chocolate chip cookies is chocolate chips. I absolutely have to have the chocolate chips in order to make the recipe work. So imagine that your chocolate chips are carbohydrates essentially, which they would be anyway. And so I have to have carbohydrates in order for the system to work. However, I can substitute in all these other things as well. Okay. And so it's sometimes said that fats burn in a carbohydrate flame. And what I mean by that is that in order for me to utilize fats in this recipe, I've got to have the chocolate chips. I've got to have the carbohydrate in order to allow the fats to be burnt. Okay, so I can use fats, I can use proteins, but I absolutely have to have carbs as kind of like a primer to allow those other nutrients to be broken down. And that's what's going to happen here within the citric acid cycle or the Krebs cycle. Okay. The last process of this aerobic pathway is known as the electron transport chain. And again, this will also occur within the mitochondria on the inner mitochondrial membrane. So again, let me draw you a little picture here, take you back to that high school biology class. Mitochondria kind of looks like a mandarin orange. Pardon my drawing skills. Okay, so the Krebs cycle that we talked about just on the previous slide occurs inside here. And the electron transport chain is going to occur on this inner mitochondrial membrane. Okay, so basically I've got like some little chambers that are set up on this membrane, and that's where this process is occurring. This is actually the first time that I'm using oxygen in the whole deal. Okay, so oxygen is only used in the electron transport chain. And now I'm going to cache in these NADH and FADH molecules that I produced in both glycolysis and the Krebs cycle. Here's what happens. So basically, I'm going to take those NADH molecules and the FADH molecules, and I'm going to shuttle them through these little transporters. And I'm going to take these H+ molecules and I'm going to take them from inside of the mitochondria into the space in between those membrane walls. Okay, and as I shuttle these H plus molecules, these electrons, okay, notice that there's a lot of pluses out here. So it's very positive in nature, and there's also a lot of them, so it's very high in concentration. Okay, so I have what's known as an electrochemical gradient. Okay, and what that means is I have a high number of these molecules, and they're also having a net positive charge in this particular area. And for those reasons, these molecules are like too crowded, it's too positive, and it's too concentrated in this particular area. So these molecules want to flow down this pump here. And so they're going to flow down this little tube, and the tube like spins around in a circle, and the spinning of this ATP synthase pump allows me to reconvert those ADP molecules that I have into ATP. Okay, so it's essentially the power or the energy from these molecules flowing down this pump that allows me to produce about 90% of the energy that we have comes from this process. Okay, and again, this process, as we mentioned, is known as the electron transport chain. So again, you know, the electrochemical gradient is what represents this potential energy. Okay, so as we mentioned, we have a high concentration. Let me get my little pointer. We have a high concentration. We also have a high amount of positivity in this particular area. And as a result, those molecules want to flow down this free chamber, causing it to rotate around. And the rotating of this chamber allows us to produce ATP. Okay, so again, as I mentioned, 90% of the ATP that we have comes from this particular system. How much energy do we get? Like I said, like a shit ton comes from this particular pathway. So each NADH will produce 3 ATPs, each FADH will produce 2. Okay, so in what sports is this particular system important for? You know, we said that anaerobic glycolytic pathway would max out between 60 to 90 seconds. So any sport that's going to last longer than that is going to at least partially rely on this electron transport chain or these oxidative pathways. Okay, so again, you know, in what sports does that entail? Certainly soccer would be a big user of the oxidative pathways. Wrestling, you know, we mentioned as a strong user of that anaerobic glycolytic pathway. They also need to have some aerobic capacity in order to make it through that third period, to make it through the full 7 minutes. Certainly, you know, all the true endurance sports, such as, you know, being a long distance swimmer, if you swam like the mile, for example, or you were a cross country runner or a distance runner in track. Again, a basketball game, you know, certainly lasts longer than 90 seconds, especially if you're good and you're playing, you know, the majority of the game. We'll certainly need this system. Okay, how is the electron transport chain affected by chronic training? You know, as we'll learn in the sport physiology class, if you haven't taken that one already, we can modify like a shit ton of things within the body with regular training, right? So we can be super diligent about what we're doing in order to kind of upregulate this system. And we can upregulate this system. Again, we talked about the mitochondria and what role that plays in these systems. Well, I can produce more mitochondria. I can have bigger mitochondria, right? So those are some of the adaptations that I can make as a trained aerobic athlete, right? So that's super cool when we think about, you know, the amount of manipulation we can have within our bodies with chronic, regular, consistent exercise training. And again, those are things that we really want to harp on our athletes about. If you're working with a sport where, you know, having a good oxidative pathway is important, man, just consistently exercising and doing those aerobic things is so important for establishing, you know, a high amount or a high capacity of this particular system, you know, way before the season even starts. Okay. So again, we talked a lot about carbohydrates, and again, we said carbohydrates are important for all 3 systems, so we can use carbs easily in any of the systems that we talked about. At the end of the day, 1 glucose molecule or 1 sugar molecule gets us about 39 ATPs. So again, here's kind of a summary of what's going on with the three systems as it relates to aerobic pathways. So first you start with glycolysis, and again, we said glycolysis involves one sugar molecule breaking down into pyruvate or pyruvic acid. Then we convert that pyruvate into acetyl-CoA. As we move into the mitochondria, we'll enter into the Krebs cycle where we get net gain of NADH and FADH. Again, Krebs cycle is our first opportunity to use proteins and or fats if we want to, but we need carbohydrates as kind of the primer to get those things started. And then lastly, we'll use the electron transport chain in order for us to utilize that oxygen molecule and to get 90% of the ATP that we have. Okay, we talked briefly about fats, and I want to spend just a little bit more time talking about how we use fats as a fuel. So lipolysis is the breakdown of fats. And what we're going to do first is we need to get those fats out of storage. And so we have fats stored basically everywhere in the body. And again, let's imagine that I'm riding my bike, for example. Okay, so I'm primarily using just my leg muscles, right? But if I'm activating lipolysis, if I'm using these kind of fat metabolic pathways, I'm not just accessing fat from my leg muscles, I'm going to access fat from everywhere in the body. Okay, and the way I'm going to do that is I'm going to release something known as hormone-sensitive lipase. And hormone-sensitive lipase is going to allow us to get those fats out of storage. And again, that storage is going to come from everywhere in the body, not just the muscles that I'm using. And I'm going to release those fatty acids into the blood. Okay, those fatty acids are then going to be carried in the blood to active tissue. Okay, and that just means like any muscle that I'm using during that exercise bout. So I'm going to carry those fatty acids to the active tissue. Those fatty acids are going to enter into whatever muscle cell that I'm using. So in the biking example, maybe they're muscles in my quads. Okay, those fatty acids are going to become activated. So we're going to have a little bit of an investment of ATP in order to kind of get those fats ready to go. And then they're going to be carried into the mitochondria for something known as beta oxidation. Beta oxidation is basically like I'm going to take a fat molecule and I'm going to I'm going to like nip off these little sections. Okay, so again, I nip off this 2-carbon bond, and that's equal to 1 acetyl-CoA. And then I'm going to nip off this section over here, and that's equal to a second acetyl-CoA. Okay, so I'm going to cleave off these little chunks of the fatty acid in order for me to get like a bunch of the acetyl-CoA molecules. Okay, you might remember the term acetyl-CoA from a previous slide, and it's the same thing. So we got acetyl-CoA from carbs. We also get acetyl-CoA from fats as well. So we're going to throw this substitution. So this is like, you know, the applesauce versus the eggs was my example before. I'm going to throw this acetyl-CoA into the Krebs cycle, even if it comes from fats. Okay, so again, this is how fats can enter into the Krebs cycle. Again, how much energy is a fat molecule worth? Well, it's worth a lot more than a carb. We said a carb was 39 ATP. We get 129 ATP out of one fat molecule. So much more dense as it relates to, you know, energy. However, it's much slower for us to activate these pathways. In order for us to really be burning fat substantially, we need to do at least 45 minutes. We need to do at least 30 minutes, 30 to 45 minutes of moderate to low intensity exercise before I'm even mobilizing fats. So it takes a freaking long time for us to activate this pathway. But once I do, I get a really nice bang for my buck as it relates to, you know, energy. Okay. So again, we think about fat utilization and sport performance. Not a lot of sports are using fat as a fuel during their actual competition. Now, certainly endurance athletes are able to mobilize fats and use fats during long workouts and things like that. And if we were to look at, you know, some of those like ultra endurance types of races and events like that, yeah, those people are using fats as a fuel source. And again, That's why those people are so lean in nature. They're such good fat burners that they barely have any body fat at all, because they're very good at mobilizing the fat that they have, right? But again, when we think about the grand scheme of things as it relates to sport performance, most athletes are not using fats during their performance. We might be using fat during our practices and things like that. And again, lots of benefits associated with using fats as opposed to carbohydrates. And we'll talk about that in lecture 3, why that would be an advantage for us, right? But again, kind of net takeaway today, we're getting a lot of bang for our buck out of these fats. However, the kind of con with that is it takes a long time in order for us to even mobilize fat and activate these pathways. Okay. So again, we think about the interaction of these 3 systems that we've talked about. It's important for us to note that none of the systems are working independently, right? So all these systems are going all the time. So when I say, an exercise that's 60 seconds in duration is going to rely on the on the anaerobic glycolytic pathway, what I mean is that pathway is dominating. That pathway is providing us with the most energy. However, we're still getting a little energy from the other pathways as well. So that's important to note, that all systems are working at any given time. It's just a matter of who's the dominant force when it comes to energy, production, essentially. Okay. So again, the phosphocreatine system is really quick to be activated, but it has a high level of fatigue. Whereas, fat oxidation, we have an unlimited amount of fat that we can utilize. We've got a shit ton of fat stored in our bodies. And again, that's not like meant to be offensive. Like, I'm not saying that you're fat. I'm saying like the average person has enough fat stored in their bodies to allow them to sustain activity for many hours. Okay. But it takes a long time for us to activate and get those sources available for us. Okay, so again, if I were to rate my energy systems as it relates to power, get my little pointer out. Again, our most powerful system is that ATP phosphocreatine system. Our second most powerful system is the anaerobic glycolytic system. Our third most powerful system is the aerobic pathway using carbohydrates as a fuel. And our least most powerful system is the aerobic system if we use fats as a fuel. Okay. Again, when I think about how much energy I have available, you can basically just flip these. Okay. Maximum energy availability, I have fats stored, and I have enough fat stored, about 70,000 calories worth of fat stored for the average person. When I think about aerobic system, the use of carbs, I have about 2,000 calories of carbs stored within the body. Okay. When I think about that anaerobic glycolytic system, if I can do exercise up to 90 seconds or so for that particular system, let's say that's around 100 calories or so of carbohydrates available readily. Is that right? We'll say closer to 200, say 200 calories for step number 3 for the anaerobic glycolytic pathway. And then when we think about, that ATP phosphocreatine system, which is going to kind of max out at like 12 seconds, maybe we have, 20 calories worth of that ATP phosphocreatine system readily available. Okay. So again, important for us to understand the difference between these systems, but also keep in mind that all systems are going to work together in order for us to achieve any task at any given time. Okay. I stopped here. So that's it for today. I hope you have a great day, and thanks for tuning in.